Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, welcome to Physics with Beth and Beth. I'm Beth. We're on AP Physics 1, Unit 8 Fluids. This is the next to last video. My colleague Beth will do the next video, also on Bernoulli's principle. So we are, in the first part of this unit, we had density, pressure, and buoyancy that were about fluid statics, where the fluid's not moving. Now we're in fluid dynamics where it is moving, and we've had the continuity equation, and now we have Bernoulli's principle. So let's talk about what Bernoulli's principle says. Bernoulli's principle says that an increase in the speed of a volume of fluid occurs simultaneously with a decrease in its pressure. All right? Sounds innocent enough. The equation looks awful, and by the way, it is the biggest equation on your AP Physics 1 equation sheet. It's the very last one, so save the best for last, I guess you should say. But we're going to hopefully make this all make sense for you, and so that we can also decrease your pressure that you're feeling about this unit, okay? Pun intended. Here we go. So what that means is an increase in the speed of a volume of fluid occurs simultaneously, if I can get that out, with a decrease in pressure. So when you increase velocity, you decrease pressure. When you decrease velocity, then you increase your pressure. That's the basic concept. Now there's also something that's going to occur if you change the height of part of this pipe. And you're going to see that in the next video with my colleague. That's also going to play a factor, this height. But we're just going to address the velocity issue now. What happens if you change velocity? My colleague in the next video is going to come in and say, okay, well, what if you have a pipe that goes up and you actually change your height in this? So she'll address that, because there's two things that can happen. I mean, there's changing in velocity or changing height will affect your pressure in the pipe. All right, let's get started. Before we get started, I really want to address what Bernoulli's principle is. I think I've told you in an earlier video, maybe not, but this fluids unit is near and dear to my heart. As a petroleum engineer for Chevron, we dealt with fluids all the time in pipes, whether it was drilling, whether it was producing oil, whether it was transporting oil, whether it was at a refinery moving product around, and not just oil, but water and gas. So I wish, and I had amazing professors, so maybe they said it and I missed it, but I wished I would have known this a little earlier, and I'm sure it was on my part for just missing it from being tired in class one day. But all Bernoulli's principle is really conservation of mechanical energy with moving fluids in a pipe. That's really all it is. And you have mastered that conservation of mechanical energy. So don't let this formula scare you. And what I mean by that, I'm going to go ahead over here. Actually, I'll go under it here and show you. Pressure, this is really just work plus your potential energy plus your kinetic energy of your fluid before a change. And then we're going to change the velocity by changing the cross-sectional area. And then it's going to equal the work plus the potential energy due to gravity plus the kinetic energy after. That's really all this equation is saying. And you're like, yeah, but you have pressure there, not work. Well, I don't understand that. I'm not so for sure I'm buying that. Instead of mgh, you have density times g times this height. I'm not for sure I'm buying that. And instead of 1/2 mv squared for kinetic, you have 1/2 density times velocity squared. So I'm not for sure I'm buying this. Well, okay, so let me show you. Work is force times displacement, right? And then we're going to divide each one of these by an equal volume of water. So because we're dealing with a volume of fluid here, it says an increase in the speed of a volume of fluid. All right, so look at this. Volume, this means volume, not velocity. And I'm going to write that out because we've got some velocities in our equation, and a big V and a little v is hard to distinguish on a whiteboard. But volume is actually, right, force times delta x. By the way, this was work, we said. Force times displacement. Volume is area times displacement, right? You can have area times h, you could say. Look, these cancel out, and we're left with force over area. Well, what is force over area? We've seen that. We saw that in some of our earlier videos in this unit. It's pressure. So this pressure is kind of representing the work that's done there over a volume of water. Okay, then we could do the exact same thing for this next one. Look, potential energy we know is mgh. All right, put it over a volume of water. So that's volume, not velocity, because we're talking about this volume of fluid. All right, well, mass divided by volume, what is that? Oh, we know that. We saw that in the first video in this unit. That's density. So that's density times GH. That's where that comes from. Density times little g, the strength of the gravitational field, times y, and we're going to measure that from the center of the pipe. That's going to be, and we're going to call that our baseline. We're going to call that 0. All right, in this equation. So then we go to kinetic energy. So we're like, oh, okay, well, we know kinetic energy is 1/2 mass times velocity squared. Divide that by that volume of fluid. Well, once again, mass over velocity, mass over volume. Let me write that out again, because again, we have two V's. 1/2 mv squared is kinetic energy, divided by that volume of water, and mass divided by volume is density. So we have 1/2 density times the velocity squared here. So that's exactly what this is saying. Your work that you put into the system, because when you work on a system, you're adding energy, right? So the work here plus your potential energy plus your kinetic energy has to equal, after that change, that was before, after, and in this instance we're going to change by changing the cross-sectional area, making the pipe more narrow, your pressure from your work plus your potential energy plus your kinetic energy. So that's all this formula is. I wish that I had gotten that a little earlier on in my fluids classes. So that's why I explain it to you. All right, now that we understand that, let's just go to this problem. I have a problem. We're just going to jump right in. Now that you know basically Bernoulli's principle is just conservation of mechanical energy over a volume of fluid. Water flows through a horizontal pipe with a cross-sectional area of 3 meters per second, 3 meters squared. That is A. We're right here at point A. We have a velocity. We have an area of 3 meters squared, and it's moving at 6 meters per second, it says, with a pressure. I'm going to go ahead and write the pressure in here at A. The pressure at A is 250,000 pascals. All right. Then it says at point B, we reduce the cross-sectional area to 1.5 meters squared. All right, that is half. We've reduced it by half. So then it says, what's the velocity at this point B? And what's its pressure? Okay, when you use Bernoulli's a whole lot of times, you have to use the continuity equation with it. Now, we just posted videos on the continuity equation before this. So feel free to rewatch those if you have, or to watch them if you have not seen them. If you didn't quite get it, you may want to rewatch them. But bottom line, the continuity equation says this. Hey, your area, cross-sectional area, times your velocity at a point, I'm calling this point 1 or point A, equals, and has to equal, the cross-sectional area and the velocity at this point 2. Or part B, and that is a lowercase v. We are talking about velocity, not volume here. All right, so I need, the first thing it says, it wants me to find the velocity at point B. Well, I've got to use this continuity equation. Okay, so I know at point A, or at point 1, we can call it 1 or A, whatever you want to call it, that my area was 3, my velocity was 6, my cross-sectional area at part 2, we said, was 1.5, and I'm looking for that velocity at point 2. All right, well, 18 divided by 1.5, and you're going to get that 12 meters per second is your velocity at this point right here. It's 12 meters per second. Okay, well, we should have known that. We could have known it without actually writing out the math. If I half my area and I half this area, I've got to double the velocity for it to equal this side. Okay, perfect. All right, now that we know that the velocity is 12, check, we've done that. That's part A. Now it says, okay, determine the pressure. Okay, first of all, we're going to use a little reality check here, a little logic. First of all, we already knew that when we lowered the cross-sectional area, that our velocity should have doubled because we halved actually our cross-sectional area. So that makes sense. It started at 6, it ends up at 12. That's a good logic check. Now I know I have higher velocity at point B. Remember, with higher velocity, we should see a decrease in pressure. Okay, so we're expecting a number that is less than 250,000 Pascal. Because we have high pressure here with a low velocity, we should have a lower pressure with a higher increase in velocity. An increase in the speed of a volume is going to occur simultaneously with a decrease in pressure. So I need to get something less than 250,000, so that's going to be a good check at the end. All right, let's get started. We just start using this Bernoulli's lovely longest equation you have on your equation sheet. So let's get going. I'm going to do it over here. I'm actually going to do it, I think, in red maybe. I'm going to start with, I'm looking for this pressure. All right, so I'm going to solve for this pressure. I'm going to subtract this little unit here that was associated with my potential energy, and I'm going to subtract this little guy right here that was associated with my kinetic energy divided by volume, and my potential energy divided by volume. So I have P1 plus my density of my fluid times little g times my original height plus 1/2 of my density times my velocity at that 1 point squared. And I'm going to subtract this little guy minus my density times little g times my height at 0.2. And then I'm going to subtract this little guy minus 1/2 my density times my velocity at 0.2. And that's going to equal that pressure that they're asking for at 0.2. Or B, we called it A, and then at 1 and B at 0.2. All right, perfect. Now I'm going to look at this. I did not change height. My height at point B is the same as my height at point A because the pipe didn't increase. You're like, well, what would it look like if there was a change in height? If there was a change in height, the pipe would actually move up like this. Like you'd have an elbow joints kind of thing, and you would have a point B up here and a point A here. And that would definitely be a difference in height. And again, my colleague's going to address that in the next video. But we don't have a change in height. This is a horizontal pipe. So that means this minus this is going to cancel out because this is going to be 1,000 because it's water times 9.81, which is little g, and my height is 0. So that cancels out. And this is the same thing, 1,000 times 9.81 times 0, because I'm at 0 as my middle of both of these volumes of fluid. Okay? All right, so those cancel out. And I'm left with pressure 1 plus 1/2 the density of water times the velocity at that 0.1 squared minus 1/2 times that density times my volume squared at 0.2 equals the pressure. All right, at 1, I've got 250,000 Pascal. My density is 1,000 because it's going to be water, and that's 1,000. They said use. Did they say that? Well, we know it's 1,000 kilograms over meters cubed. All right, 1,000. And then the velocity 1 is 6 squared. And they would have told you in the problem. They're not going to ask you to memorize that, is my understanding. And that they're going to give you what the density of water is. Okay, so that velocity of 0.1 was 6, and you square it, minus 1/2 times your density, which is 1,000, times that velocity at 0.2, which we just solved for is 12. Don't forget to square it, equals P2. Don't forget these squares. It's easy to do when you're rushing through an AP exam or your exam in class. Don't forget those squares because it is tragic. If you understand Bernoulli's principle and you've understood continuity equation and the only thing that kept you from getting the right answer was forgetting these squares. That's just tragic. Nobody wants that. All right, so when I go to do that, I'm going to end up with a number of 100, that P2, by the time you do all that ugly math and you add this and then subtract this to 250,000, you're going to get that that's 196,000 Pascal. And did the pressure decrease? We were expecting with that increase in speed of 12, from 6 to 12, that we should see a decrease in pressure. And we did. It went from 250,000 pascals to 196. So it followed Bernoulli's principle. That gives us a good logic that hopefully we can feel pretty good we got the right answer there. And that is Bernoulli's principle. Again, don't forget to watch the next video because my colleague's going to talk about how height. We didn't talk about height. Our height was the same, so they canceled out. She's going to do one where the velocity stays the same, so they don't change the cross-sectional area, but they change the height so that you can see what happens then. Spoiler alert, with an increase in height, you get a decrease in pressure. Spoiler alert. And my colleague Beth does an amazing job of describing that, so be sure to watch the next one, which also happens to be the very last video of this entire curriculum for AP Physics 1. Thank you so much for sticking with us through this whole curriculum. We're so proud of you. We're so thankful for you. We know you're going to crush that AP exam and put lots of pressure on it, crush it, pun intended. And if you like this video, give us a thumbs up. If you haven't subscribed, we would love that. Tell your friends. If you find these videos helpful, we would love that too for you to share. Thank you for watching and happy physicsing.